All right, in this lecture, we're going to go over two examples that deal with energy. And the first one's from Knight, number 39. It says, in the activity of winter tubing, the rider in his tube with a total mass of 80 kilograms. Let me go ahead and get my highlighter here. Total mass of 80 kilograms are pulled at a constant speed by a tow rope that maintains a constant tension of 340 newtons. How much thermal energy is created in the slope? So we want to know delta. We want to know, let me see here. We want to know thermal energy, which we said last time. Delta E thermal, or we also called it delta U internal. Remember, U is our symbol for potential energy. And that both of these, right, are equal to, I'm going to go with delta E thermal. Both of these are equal to the force friction kinetic times the distance. All right. So anyways, how much thermal energy is created in the slope and tube during the ascent of a 30-meter high hill, okay, and in a 120-meter long slope? So a quick sketch here. We can see that this 120 meters is going to be the distance that we're traveling and generating this force friction. So this is going to be our value for D. And I think what students want to do, or the first time maybe I attempted this problem, right, I was like, okay, well, there is a constant tension, which is equal to 340 newtons. And since the tube isn't speeding up, then there has to be an opposing force, which is force friction kinetic, which is equal to 340 newtons. All right, pretty simple. And but this is wrong. But if we follow this, right, and we keep going here, we can see where a student would say delta E thermal is equal then to 340 newtons times 120 meters, and end up getting an answer here of this is 40,800. And this is wrong. All right, so I wanted to point this out and do the example the correct way and talk about what broke down. Where is the logical mistake? And maybe you can already see it. But let's point out why it's wrong here. So let's go ahead and do this problem a different way. Let's do it like this. It says, write a formula for the energy balance. Hint, Ke equals 0 for both initial and final, as it's the same on both sides of the equation. All right, so I'll mention that in a second. It's not really equal to 0, but it's gonna cancel off. So let's go ahead and write this. So initially, what kind of energy do we have? Well, the tube is moving initially. And since it's pulled at a constant speed, that's kind of what we have to go with, is that the Ke initial is going to equal the Ke final. So I'm going to go ahead and write Ke initial here and Ke final here, but knowing full well that they are the same. Maybe I should switch over to black here, just so it's different from my wrong answer up there and it's not too confusing. All right, since that's true, I'm going to go ahead and still write it in. It's fine. We also know there's that we have to pick a system here, and the question is, and this is kind of like why we're doing these problems, right, is getting used to picking systems, getting used to identifying types of energy. That's where these problems are tough. It's not so much in the math, right? The math is kind of easy, but it's the identifying the types of energy and picking our system correctly. And if delta E thermal exists, and we want it to because we want to solve for it, then force friction has to be internal to the system. If force friction is external, then it does work on its own, and it can't do both. You can't either force friction is going to be external and do work, or you're going to have delta E thermal. So we want delta E thermal. So I'm going to go ahead and write that on the final side. And this means that the ground is part of the system. So if I'm going to label my system, let's see here. My system should be the person and tube plus the ground, right? Okay. So yeah, we can go ahead and just call that the earth down there, and that's fine because we are going to have gravity here as well, right? The person's going to start at the bottom of the hill, so there won't be any potential energy initial, but when they get to the final part, there is going to be potential energy gravity. Okay. So there's one more type of energy we have to remember here, and that is there is an external force that is going to do work. And hopefully you can see what that is. That's going to be the work done by tension. All right, so this is going to be our energy equation. Once again, initial kinetic energy initial and kinetic energy final are the same, so they can cancel off. You can subtract them from both sides, and they go away. So we're left with this. The work done by tension is equal to delta E thermal plus the potential energy of gravity. Now, we want to know delta E thermal, so we aren't going to separate this into force friction times distance. And we don't know force friction. We do know the distance, so we're just going to leave it like that, right? So I'm saying right here, we're just going to leave this guy the way it is. But let's go ahead and break the other ones into parts, because that way we can put numbers there. So we know that work tension is equal to, work is always FD cosine theta. So we're going to have the force of tension, right, which we'll just call T, times the distance times the cosine of theta. All right. Well, what is theta? That's going to be a little tricky. We'll have to look at that. So I have delta E thermal plus the mass times baby G times the height. Okay. So let's go. What is theta? Well, theta is the angle between the force T and the distance D. Well, we might have to do some trig here, right? We do know two sides of this triangle, but do we have to or not, right? Let's think about this. So what we have here then is we have the inner tube, right? If I just draw it over here, and it's being pulled by the force tension over a distance d. So as long as our distance is 120, we don't have to worry about an angle. You see that? So theta is going to equal 0. All right, so let's go ahead and come back over here and plug those in. So we're saying 340 newtons times 120 meters times the cosine of 0, which is just going to equal 1. Delta E thermal. What about our mass? I think they told us that the tube plus the person is 80. I gotta go back up and look. Total mass of 80. Okay. And the height of the hill was the 30 meters. Okay. Good. So now we can go ahead and plug in some plug this into our calculator and get some numbers. I may already have these values crunched somewhere. Let's see, I think I do. 40,800. All right, there's that answer that we said before, right? That was our delta E thermal, but we're seeing right now that it's not going to be. This is 23,544. All right, we'll subtract that 23,000 from both sides. We're going to end up getting a much smaller answer than the incorrect one. All right, so what's going on here? Why is this the right answer? And the shortcut method up above didn't work, right? The 40,800. What happened? Well, let's go down here. Here's our mistake, and hopefully you spotted this before. Friction kinetic does not equal tension, right? But why? It's moving at a constant speed, so it's in equilibrium. Well, you have to remember, right? When you have to draw your free body diagram. And I think that is the problem that I made when I first did this, and I could see, and I think students made in the past too, and that's why this ended up in a note guide, right? So we have tension here. We have force friction kinetic, which is going to end up being smaller. But what other forces are there, right? Well, there's force normal. But then we have one more force, right? And it's this oddball force because it's going to point in a direction that doesn't agree with our coordinate system, and that's force gravity. So when we have these forces that don't line up like this, we have to pick a coordinate system. Do we stay with up, down, left, and right, or do we switch to a tilted axis? And the tilted axis is definitely the way to go here. So we split force gravity into a down and a left. And you got to practice drawing this triangle if you can't do that, because that's an important skill to have. It creates a 90-degree angle, but what we see is we have an FGY and an FGX. And because of the way the geometry works out, this angle right here is equal to this angle right here. So we can call this theta and this theta. I'll go ahead and color them yellow. Okay, so sure. So that's what we have here. So my point is this, right? If we do Newton's second law in the x direction, we can see where our logical mistake happened. So sigma fx is equal to 0. Let's go ahead and draw our coordinate axis system so you can see. We'll call this direction positive x, negative y, positive y, like that. That's our tilted axis. So let's go ahead and say then tension minus force friction kinetic minus our additional force, which we forgot about, that we logically assumed wasn't there last time, that we now can see is there, which is FGX. And that's equal to 0. And therefore, tension then does not equal force friction kinetic, but equals force friction kinetic plus Fg of x. And so we can see then that if we rearrange it, I probably should have just rearranged it to calculate force friction kinetic then, we can see force friction kinetic, which we said is equal to tension, is actually equal to tension minus FGX. All right, and that's kind of the key point, right? That we used friction kinetic equal to tension. All right, so let's go ahead and plug in some numbers here. So we have 340 newtons for tension minus Fg of x. What is Fg of x? Well, Fg of x is an op. Fg is a hip. Right, here's your 90-degree angle. All right, so sine theta equals op over hip. Sine of theta then is equal to fgx over fg. Fg of x is equal to fg sine theta, which is equal to mg sine theta. All right, so we can go ahead and what is mg sine theta then, right? It is, let's go ahead and write it down here so I have a little more room. Instead of writing at an angle like that, it's obnoxious. The mass is 80. Oh, we don't know theta though. That's a problem. Coming back up here, I think we can do a little trig there to get the, based on this hill, right? We know hill looks like that. This is 120. This is, was it 30? I think it was 30. Okay. So, and we want to know theta. This is an op. This is a hip. We can use inverse sine. So, remember sine theta equals op over hip. Sine inverse will cancel off sine. But you have to do it to both sides. So we're left with theta equals sine inverse op over hip. Theta then is equal to the sine inverse of 30 meters over 120 meters, which is what, 0.25? That's a fourth, yeah. So inverse sine of 0.25 gives me a 14.48 roughly. Okay, so then we can go ahead and bring that down here. Okay, and then we can go ahead and plug that in our calculator. I think I may already have this crunched somewhere. When we do this, we end up getting 196.23. Newtons here. And what we were solving for over here, if you remember, is force friction kinetic. All right, so we do the 340 minus the 196, and we see the force friction kinetic is actually equal to 143.77 newtons. All right. Okay, so this then is the number we should have plugged in originally. So if we go back now to what we originally, our mistake we originally made, where was it? Right here. Okay, if we go back and do the right thing, so we make this 143.77 newtons. It's kind of hard to read. What is 120 times 143.77? It is 17,252.4. I wrote newtons here earlier. Oh, whoops. Let's correct that too. It was double wrong. All right, joules. And does that agree with what we had from doing it the correct way down here? And it does. So you can see now that this is correct. All right, good. So hopefully that makes sense why on these problems where an object is on a hill, don't forget about gravity. It is contributing. It is a contributing force on the hill, and that was the mistake that was made here. Okay, because it's FGX component is opposing tension as well, right here, right, in addition to force, friction, kinetic. All right, so draw the free body diagram out, and you can see that. Okay, in the next example, that says a spitball is shot from a straw that is a couple centimeters from a block of wood that is hanging from a string. The spitball mass is 10 grams. Right away, we don't like 10 grams, so we're going to switch that into kilograms. The mass then of, we'll call this mass of the spitball is equal to 0.01 kg, right? Okay. And it sticks to the 1 kilogram wooden block. So if it sticks, we know this is a inelastic type of collision, which swings upward to a height of 0.2 meters. So the block is just hanging there, but then it's going to move to this upward position like a pendulum. What is the speed of the spitball upon leaving the straw? So we want to know, if we go down here and look at this, what is the, and I think I should have wrote MSB here. Okay. We want to know what is this initial speed right here, VS initial, right? And I guess I'm using, I should probably just say VSB initial, right? And now we don't have two different abbreviations for spitball. Okay, and the block can be just B. All right, that makes more sense. All right, so we want to know what this initial speed is before the impact, before the collision. So we should be thinking here collisions. Whenever we think collisions, really think conservation of momentum. I know that shows up a lot on the AP test where there'll be a collision, but the AP test won't go out of their way to say there's a collision. They just want you to recognize it's a collision and then apply conservation of momentum, but sometimes students forget that. So let's go ahead and balance our momentum. We can say then PI is equal to PF. And we know that initially only the spitball has momentum because the block is just sitting there. So you have the mass of the spitball times the initial velocity of the spitball, which we want to know. That's the whole point of the problem. Plus the mass of the block times the initial velocity of the block. Let's see, go VB comma I. Let's do that. And that is 0. So this whole thing is going to be 0. All right. Then finally, the masses combine, right? Because the spitball sticks to the block. And they move with one final velocity. We'll just call it, let me just call it VF. Sure. All right, but we don't know what VF is, and that's a problem. So I'll go ahead and rewrite this. So we have the mass of the spitball, which is that 0.01. Whoops, can't write a 1. Geez, I'm going to do that over. 0.01 kilograms times VSB. And that's going to equal the mass of the spitball plus the block. Isn't the block just 1 kilogram? So this is going to be 1.01 kg. All right, that sounds reasonable. All right, so here's our problem, right? I just kind of wanted highlighter there. 2 variables, or 2 unknowns. We can't solve for the velocity of the spitball initial. So we need 2 equations. So we do know a little bit more, right? And that's kind of the idea here. What they want you to see is that this is over here is an energy problem, right? You have an object moving with some initial KE, right here. So there's some KE initial. And at some later point, it's going to get all the way to the top of this pendulum, kind of like, right? and you're only going to have potential energy gravity. So you can call this right here, where the pendulum is hanging from, you can call the bottom 0. And that's the key idea, right? That this final position of 0.2 meters, that means that this height is going to equal 0.2 meters. And so therefore we know the total energy in this problem, right, is either the total kinetic energy at the bottom or it's the total potential energy at the top, which we know because we know this is equal to mgh final. And we know h final is 0.2 meters. We know g, we know mass is 1.01. And so we can work backwards here to get the kinetic energy initial, because we really want to know the velocity of the spitball plus this should be spitball plus block, right? Because we called velocity of spitball plus block, I think we called it VF, right? So that's kind of confusing. So what I'm trying to say here is that the velocity of the spitball plus the block is the VF part 1, right? This is the VF from down here. This is this. So the initial velocity in this energy balance, right, is equal to the final velocity from the momentum balance. Okay, I think that makes sense. So hopefully it makes sense to you. All right, so let's go ahead and so what are we going to call this dang velocity? Let's just stick with VF, right? And hopefully, so I'm saying we're going to stick with this being the same as this. All right, and hopefully that makes sense why we're doing that. Okay, so let's go ahead and write our energy balance here. So we can say EI equals EF. We can say that in the beginning we only have kinetic energy initial, and in the end we only have UG final. You don't have to call it final initial, but I kind of just liked, I don't know, sometimes it's just a habit, I guess. Kinetic energy initial is equal to 1/2 m. Instead of VI, I'm going to call this, well, I'll call it VI right now, but I'm going to put a VF there, and hopefully that makes sense why. All right, and here I'm going to go mgHF. And so what I'm saying is this will be 1/2 the mass, which is that 1.01, right, because it's both things combined, times VI, but we're going to call it, like I said, I'm going to call this VF, and this is squared, right, because this is the same VF from here, right? Okay. All right, so anyways, hopefully that's, is equal to 1.01. Oh, I could have just, I don't know why I'm writing the mass, right? It's just going to cancel away. Oh, well. I'll still cancel it away. And the height there was 0.2. Yeah. Which I guess is 20 centimeters. Is that what they said? They just gave us 0.2. They didn't even make us think about it that hard. Okay. So we'll go ahead and cancel off the masses. All right, that makes it a lot nicer. So we can then say, let's just rewrite. This is kind of tough to look at. All right, so let's do a little math here. Multiply both sides by 2, and then square root. So I think we're going to end up getting VF is equal to the square root of 9.81 times 0.2 times 2. All right, so if we plug that mess in our calculator, I don't know if I already have this crunched. I think I do. I think we should be getting 1.98. I kind of want to just double check because I haven't done this problem in a while. I'm getting 3.924 under that square root sign. So the square root of 3.924, yeah, 1.98. Okay. All right. So, all right, that's good. Let's go ahead and take that number then, and let's just move it right there. That's all we're doing. So, and then this problem should get really simple. Okay, so we'll say then VSB comma I, will divide this 0.01 over there, is equal to 1.01 kg times 1.98, which we just are subbing in, divided by 0.01 kg. All right, and that should give us meters per second for units, because you can see those kgs canceling off. And when we do the math there, we end up getting spitball, pretty insane velocity. Ends up being, I think, 199.98 meters per second. And I forget why it's so crazy. I think I don't know if the book had an explanation for that or why, but it's obviously unrealistic. I think because the idea is, I mean, 1 kilogram, that's 2.2 pound block, right? And you got a spitball which has a mass of 10 grams. So in order to hit a 2.2 pound block with a 10 gram object, you really got to be cruising, right? This is like 450 miles an hour. Something crazy. So anyhow, there you have it. So there's our final answer right there. All right, I really like that problem because it combines the two chapters. These conservation laws are really important to physics and really important to the AP test. And so this is a great problem for that reason. And yeah, and so it's definitely a good one to go over. Sorry I didn't use this page under here. It's just annoying having to flip pages. So at one point I thought that was the right way to do it, but I think it's just much easier to keep it all on one page. All right, anyways, that's the end of the lecture. Have a good day.